Okay, so that will integrate to 1/2 of sine 2 theta from 0 to pi over 4, sorry. And sine pi over 2 is 1, so you will get 1/2. Okay, any questions about this one? No? Okay, then let's do the third one. So the third guy is when we come back to the origin along the diagonal. Okay, so we go in a straight line from this point. Where's this point? Well, this point is 1 over root 2, 1 over root 2. And we go back to the origin. Okay, so we need to figure out a way to express x and y in terms of the same parameter. So one way, which is very natural, would be to just say, well, let's say we move from here to here over time. And, you know, at time 0 we're here, at time 1 we're here. We know how to parameterize this line. So what we could do is say, let's parameterize this line. So we start at 1 over root 2, and we go down by 1 over root 2 in time 1, and same with y. That's actually perfectly fine, but that's unnecessarily complicated. Okay? Why is it complicated? Because we'll get, you know, all of these expressions. Would be easier to actually just look at motion in this direction and then say, well, if we have a certain work, if we move from here to here, then the work done moving from here to here is just going to be the opposite. Okay? So in fact, we can do slightly better by just saying, well, we'll take x equals t, y equals t, t from 0 to 1 over root 2, and take, well, sorry. That gives us what I will call minus C3, which means C3 backwards. And then we can say the integral for work along minus C3 is the opposite of the work along C3. Or, you know, if you're comfortable with integration where variables go down, then you could also say that t just goes from 1 over square root of 2 down to 0. And, you know, when you set up your integral, it will go from 1 over root 2 to 0. And, of course, that will be the negative of the 1 from 0 to 1 over root 2. So it's the same thing. Okay, so if we do it with this parameterization, we'll get that, well, of course, dx is dt, dy is dt. So the integral along minus C3 of y dx plus x dy is just the integral from 0 to 1 over root 2 of t dt plus t dt. Sorry, I'm messing up my blackboard. Okay. Which is going to be, well, the integral of 2t dt, which is t squared between these bounds, which is 1/2. That's the integral along minus C3, along the reversed path. And if I want to do it along C3 instead, then I just take the negative. Okay? Or if you prefer, you could have done it directly with integral from 1 over root 2 to 0, which gave you immediately the negative 1/2. Okay, so at the end, we get that the total work was the sum of the three line integrals. I'm not writing f.dr just to save space. That's 0 plus 1/2 minus 1/2, and that comes out to 0. So a lot of calculations for nothing. Okay, so that should give you a good overview of, various ways to compute line integrals. Any questions about all that? No? Okay. So next, let me tell you about how to avoid computing line integrals. Well, one is easy. Don't take this class, but that's not. So here's another way not to do it. Okay? So let's look a little bit about one kind of vector field that actually we've encountered a few weeks ago without saying it. So we said when we have a function of two variables, we have a gradient vector. Well, at the time it was just a vector, but that vector depended on x and y. So in fact, it's a vector field. Okay? So here's an interesting special case. Say that f, our vector field, is actually the gradient of some function. So it's a gradient field. And so f is a function of two variables, x and y, and that's called the potential for the vector field. The reason is, of course, from physics. In physics, you call potential, well, electrical potential or gravitational potential, or potential energy, this function of position that tells you how much actually energy is stored somehow by the force field, and its gradient gives you the force. Actually, not quite. If you're a physicist, then the force will be negative the gradient. So that means that physicists' potentials are the opposite of a mathematician's potential. Okay, so that's just here to confuse you. It doesn't really matter, but so to make things simpler, we are using this convention, and you just put a minus sign if you're doing physics. So then I claim we can simplify the evaluation of the line integral for work. Okay? So perhaps you've seen in physics the work done by, say, the electrical force is actually given by the change in value of a potential from the starting point to the ending point. Or same for gravitational force. So these are special cases of what's called the fundamental theorem of calculus for line integrals. So the fundamental theorem of calculus, not for line integrals, tells you if you integrate a derivative, then you get back the function. And here it's the same thing in multivariable calculus. It tells you if you take the line integral of the gradient of a function, what you get back is the function.